There is a hole in the universe. Not a black hole, something far stranger and far larger. A region of space 330 million light-years across that contains almost nothing. No galaxies, no gas clouds, no clusters, no visible matter of any kind. Just absence. Astronomers stumbled onto it in 1981 while mapping the distribution of galaxies, and for a moment they assumed they had made an error. The error was not theirs. The hole was real. It is called the Boötes Void, named after the constellation in whose direction it sits. And the reason it matters is not just that it exists, it is that according to everything we understand about how the universe forms structure, something this empty should not be possible. We begin. The universe, at large scales, looks like a web. Vast filaments of galaxies stretching across hundreds of millions of light-years, connecting at enormous knots called clusters, with empty regions in between. This structure grew from tiny fluctuations in the density of the early universe, amplified over 13 billion years by gravity. Matter pulled toward matter. Dense regions grew denser. Low-density regions emptied out. The result is what astronomers call the cosmic web, and within that web, voids are normal. Every region of relative emptiness you see in the large-scale maps is a void of some kind. Most of them are 20 to 50 million light-years across. The Boötes Void is 330 million, 6 times larger than any void our best models say gravity should be able to produce in the time the universe has existed. This is not a small discrepancy. It is a problem. Here is how voids are supposed to form. In the early universe, some regions were slightly less dense than average. Not much less. A tiny fluctuation, smaller than 1 part in 100,000. But gravity is patient. Over billions of years, matter flows away from underdense regions toward overdense ones. The underdense region grows emptier. Slowly. The problem with the Boötes Void is the timescale. The universe is 13.8 billion years old. Even with dark energy accelerating the expansion and helping voids grow faster, standard cosmological simulations do not produce a void this size in this amount of time. Either the void formed through some process we do not understand, or several smaller voids somehow merged. Or our model of how structure forms is missing something. All 3 possibilities are uncomfortable. None is resolved. But here is the stranger part. The Boötes Void is not completely empty. A small number of galaxies exist inside it. About 60 have been confirmed. And when astronomers studied them closely, they found something unexpected. These galaxies are different. They are bluer, which means they are forming stars at a higher rate than average. They are less evolved, more irregular in shape. They look like galaxies that grew up without interference, without the gravitational pressure of neighbors, without the mergers and collisions that reshape most galaxies over time. They are simpler, younger looking. They are what a galaxy becomes when the universe leaves it alone for billions of years. They are the control group in an experiment nobody designed. In 2004, the WMAP satellite produced the most detailed map ever made of the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. It was supposed to be almost perfectly uniform, with tiny variations of 1 part in 100,000. And it was. Except for one region. A patch of sky significantly colder and larger than anything the standard model predicted. Astronomers called it the cold spot. It sat in the southern sky, in the direction of the constellation Eridanus, and it was not subtle. It was cold enough and large enough to be statistically improbable by a significant margin. The first explanation most researchers offered was instrument error. It was not instrument error. The Planck satellite confirmed it in 2013 with better data. The cold spot is real. One explanation for the cold spot involves a supervoid aligned between us and that region of the cosmic microwave background. When a photon of light travels through a void, it gains energy entering and loses energy leaving. Under normal circumstances, those effects cancel out. Net change, zero. But in a universe with dark energy, the void expands while the photon is crossing it. By the time the photon exits, the gravitational well it climbed out of is shallower than the one it fell into. The photon loses a tiny amount of energy. This is called the integrated Sachs-Wolf effect. If a void large enough is lined up between us and a region of the cosmic microwave background, it would leave a cold imprint. A photograph of emptiness pressed onto the oldest light in the universe. Measurements published in 2015 found exactly this. A supervoid in the direction of the cold spot, roughly 1.8 billion light-years across and 3 billion light-years away. The largest underdense region ever detected. And it was still not quite large enough in the models to fully explain the cold spot on its own. There is a second explanation, a more radical one. In the theory of eternal inflation, the universe we inhabit is one bubble among a vast number, each nucleating from an inflating background that never stops. Our bubble expanded, cooled, and became the cosmos we see. But in eternal inflation, bubbles occasionally collide. The collision of two bubble universes would leave a circular imprint on the cosmic microwave background of the surviving bubble. A bruise. The cold spot is circular. It is cold. It is large. It is in the right part of the sky. None of this proves a bubble collision happened, but none of it rules it out. We have one data point that is consistent with contact between our universe and another one. We do not know what to do with that. Behind all of this sits a deeper question about the entire framework of cosmology. The cosmological principle states that the universe, at large enough scales, is homogeneous and isotropic, the same in all directions, the same from all locations, no preferred place, no preferred direction. This is not an observation, it is an assumption. An assumption built into almost every equation in modern cosmology. And it is an assumption the universe keeps challenging. The Boötes Void challenged it. The cold spot challenges it. And then, in 2013, astronomers mapping the distribution of quasars found something that challenges it at a scale that is genuinely difficult to process. The Hercules Corona Borealis Great Wall. A structure of galaxies and quasars approximately 10 billion light-years across. 10 billion. The observable universe is 93 billion light-years wide. This single structure spans more than 10% of everything we can see. By the cosmological principle, structures this large should not exist. The universe should have become smooth and featureless at scales above roughly 1.2 billion light-years. This structure is 8 times beyond that limit. The discovery was made through mapping gamma-ray bursts, the brightest explosions in the universe, which are visible across cosmic distances. The clustering of those bursts in one region of the sky revealed the outline of something that our models say should be impossible. The response from the cosmological community was measured, not dismissal, but deep uncertainty about what it means. Here is the problem that sits underneath all of this. Our observable universe is not the universe. It is the part of the universe from which light has had time to reach us in 13.8 billion years. Beyond that horizon, space continues. How far, we do not know. Whether it continues forever, we do not know. What structures exist beyond our horizon, we have no way of determining, because no signal from there has ever reached us, and no signal from us will ever reach there. The cosmological principle may be perfectly true at scales beyond what we can observe. The universe may become smooth and featureless 100 billion light-years out. We have no way to test that. We are inside a sphere of visibility, trying to describe a universe that may be arbitrarily larger, using data from the one small region we can access. Go to the other extreme. Go small. At the quantum level, there is no such thing as empty space. The vacuum is not empty. It seethes with what physicists call virtual particles, pairs of matter and antimatter flickering into existence and annihilating each other in intervals too short to directly observe. Every point in space, including the deepest center of the Boötes Void, is filled with this quantum foam. The zero-point energy of the vacuum is not zero. It is a specific, non-zero value at every point in the universe. This is not philosophy. It is measurable. The Casimir effect, the tiny attractive force between two uncharged metal plates placed extremely close together in a vacuum, exists because of this. The plates exclude certain wavelengths of virtual particles from the space between them, creating a pressure difference. The void pushes. Even at its emptiest, space cannot stop moving, and this creates the most embarrassing problem in all of physics. The observed value of dark energy, the energy density of empty space that is driving the accelerating expansion of the universe, is measured from cosmological observations. The predicted value of the zero-point energy of the quantum vacuum is calculated from quantum field theory. These two numbers should be the same thing. They are not. They differ by a factor of 10 to the power of 120. 1 followed by 120 zeros. That is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. Either quantum field theory is wrong about the vacuum, or cosmology is wrong about dark energy, or both are missing something fundamental. Nobody knows which. The void is literally the site of the deepest unresolved conflict between our two most successful theories of physics. Project forward. The accelerating expansion continues. Galaxies that are currently visible to us, thousands of them, cross our observable horizon every billion years, pulled beyond the reach of light by the stretching of space. In 100 billion years, the Milky Way and Andromeda will have merged, and nearly every other galaxy will have disappeared from our sky. In 1 trillion years, even the merged galaxy will have consumed most of its star-forming gas. New stars will stop forming, old ones will die. The universe will enter what cosmologists call the degenerate era. What remains will be white dwarfs, neutron stars, black holes, and cold dark matter. Over an almost incomprehensible span of time, even those will decay. The black holes will evaporate through Hawking radiation. The void will win. Not as an anomaly, not as an exception, as the final state of everything. Come back to the beginning, to the whole. The Boötes Void sits in the direction of a constellation most people have never looked for. It contains nothing you can see from the ground, nothing you can photograph without a large telescope and a very specific kind of map. And yet it matters. Not because of what is in it, because of what it reveals about the universe we live in. The universe is mostly void. The cosmic web looks solid in diagrams, but the filaments are thin and the voids between them are vast. The matter we can see, the stars and galaxies and everything we have ever named, is a thin skin stretched over an enormous emptiness. And that emptiness is not a failure of the universe to fill itself in. It is what the universe is. The web is not the structure. The void is the structure. The web is what grows in the gaps between the nothing.